We are continuing with the second tutorial. We are still solving the midterm exam, but now the remaining numerical problems. So let us see question 4A of the midterm. Draw a rough engineering stress-strain graph for an alloy steel and show at least 6 mechanical properties on this graph. Right, so it is a simple exercise that draw a rough graph, rough sketch, no actual values and so on, and for any alloy steel which is a standard material and so on, and show at least 6 mechanical properties on this graph. So again, please go ahead, do it on your rough before you proceed and see the solution. So I am showing you the solution now, that this is my hand-drawn rough graph, right? Sigma on one side, a strain on the other side, a stress and a strain, and roughly this type of a graph is there. So this is a rough stress-strain graph. Then on this graph, here I show the slope E, here I show the point sigma y, here I show the point UTS. From here to here, I show shaded area of the triangle as UR. From here all the way, right, all area under the curve I show UT, and here I show epsilon F, fracture strain, percent elongation. So these are the values. E is the Young's modulus or the elastic modulus, sigma y is the yield strength, UTS is the ultimate tensile strength, sigma F or percent elongation is the ductility, right, ductility. UR is the modulus of resilience, UT is the modulus of toughness. So we are showing 6 different mechanical properties on the same graph. So many of you did it pretty nicely, some of you were not very clear, some of you did not have an idea of the question, but generally this is the solution. And if this type of thing is there, so if you have understood during the lectures and solution and so on, then doing these small sketches yourself is not a big issue, and identifying all the properties that are there on the graph. This is question 4B of the midterm. Draw in a unit cube the crystal plane that has the Miller indices 302 bar. Right, so again, very simple question. The Miller indices of the plane are given. Draw a cube, and on that cube show this plane, and of course indicate all the distances and so on. Remember, the very first line of the midterm always says that show all details, all calculations, everything. So it is not just that you show the plane, but you should show all the distances, and if you have moved the origin to some place, then show those things. So please go ahead and do this exercise. We have done lots and lots of examples of drawing planes in the classes and so on. So do this, and once you are sure, then see the solution. So you see, this is a cube, this is a cube, this is the origin. Originally this is the origin. Now if I have 302 bar, then I take the reciprocals. You see, these numbers represent, if you remember Miller indices, the numbers represent the intersection on the axes that you see on the x-axis. On the x-axis, where is the plane cutting? On the y-axis, where is the plane cutting, and so on. So you do the reciprocals. 3 is 1 by 3, 0 is infinity, minus 2 is minus half. So these are the actual intercepts, and infinity means it does not cut the y plane. It is parallel to the y plane, but it cuts the x plane and the z plane. So, right, so now these are the numbers. As soon as it is z minus half, remember, you move the origin from the origin to the end of the z axis. This is the standard technique, that any of the Miller indices numbers is minus, then on that axis move, right, so that so because there is only one negative number which is on the z axis, your original was here, this is x, this is y, this is z, so you move the origin from here to there, so that now you can easily find the negative numbers. Otherwise from here you cannot find the negative, it will be outside the box. So now it is there. On the x-axis, this is the x-axis, right? But you are coming from there now, right? So on the x-axis, mark a point plus 1 by 3, plus 1 by 3. On the y-axis, no mark. On the z-axis, minus half, minus half. Z-axis is here, right? Z-axis is here. From there to here. So minus half on the z-axis. So now you have 1 point there and 1 point here, right? On the x-axis, plus 1 by 3. On the z-axis, minus half, isn't it? So then you just have to see that, you see, this is your plane. This is your plane, right? This is your plane, and you have now shown all the details. You have shown this working, that you have to take the reciprocals. You have shown that you have moved the origin there. You have shown that here it is plus 1 by 3. You have shown that here it is minus half, and this is the answer. So if there is any problem where you have to draw the plane and so on, then this is exactly what we require. Let us now move to part 4C of the midterm. It was divided into small portions. So this problem says the D422 interplanar spacing in an FCC metal is this number, nanometer. What is its lattice constant A? What is the atomic radius of the metal? What is the name of this metal? What is the name of this metal? So once again, right, you read what it is given. D422 interplanar spacing is given. The value is given. It is given that it is an FCC metal. So these two are given, and then you have to find the lattice constant A. You have to find the radius R, and you have to name which metal this is. So now if you are here, then you have already solved it. So let us see the solution. This is very simple, right? A is dHKL upon h squared plus k squared plus squared under root. So you just substitute the values. dHKL is given, and the plane indices are 422, right? So this is the value of the lattice constant in nanometers. So this is a very simple calculation. R, because it is FCC, right? So A is equal to 4R upon root 2, or R is equal to root 2 upon A by 4, right? Root 2A by. So you just substitute the values and you find the value of R as 0.144 nanometer. So these are very simple. That is why this question was divided into a few pieces A, B, C, that these are very simple questions. Now you have found the lattice constant A, and using lattice constant you have found the radius. Now you have the formula sheet where in the end all materials with their A values, R values and so on are given, or you have access to. So I will give you that which material is this one by the help of the table that we had. Otherwise you will have the formula sheet. So you see, you have this FCC table. You have this FCC table, and it is 0.144, right? Atomic radius is 0.144. So 0.144 is this one, and 0.144 is this one, these two. But the radius is 0.409, right? So this is 408, and this is 409. So gold is also very close, but this is 40856. So if you round off, this 6 will become 6 and this will become 9. So instead of gold, you are much closer to silver, right? So if you have written gold, you are slightly wrong. But if you have written silver, you are exactly right according to this. Let us now move to the last and final question of the midterm, question 5. The aluminum rod in the figure has diameters of 20 and 15 millimeter, and it is subjected to an axial load of 10 kilonewtons. It is already given, right? This dia is given, this dia is given. This is shown in the diagram already. A portion of the stress strain diagram of the material is also shown. This diagram is given that this is an aluminum alloy, and the stress strain graph of the aluminum alloy is given. Elastic modulus is 70 gigapascal. You see, elastic modulus will be here, but the elastic value model is already given. And if you see, the yield strength of the metal, 40 megapascal, is also given. So the yield strength is given, the elastic modulus is given. Determine the approximate elongation of the rod when this load is applied. Of the full rod, right? Not of one portion, not of the other portion. The elongation of the full rod when this load is applied. This is very critical, when this load is applied, not when this load is removed. You see, we can apply this load, it can go to the elastic region or to the plastic region, and later on the load can be removed. In that case, the final elongation will be changed. But during the load being applied, so here we are saying when the load is applied. So this is important, that the load has not been removed. The load is there. So when this load is acting, then what is the elongation? Elongation means the change in length. Elongation, the change in length. It is not the strain and so on, right? So I have already explained this to you, my bad, as they say in the current English. Otherwise, I should say my mistake. So otherwise, I would have said that please now read the question, solve it yourself, and so forth. So when you go to the next slide, then it means that you have done your level best. You have practiced this problem again, and then you go to the solution. So there it is, right? Now in the AB region of the load upon area, force upon area is the stress. So this the load is this, and pi r squared. Remember, if dia is given, then this is half. So in the AB section, 31.83 megapascal. In the BC section of the rod, force upon area, force is the same, but the radius is different. Again, this is half of the dia. This is 56. So now, if you notice that the yield strength of the material is 40 megapascal. 40 megapascal. So in AB, in part AB, the maximum stress is less than the yield stress. So the elongation is elastic elongation. This is just one part, right? And here 56.59 is more than 40. So therefore, in part BC of the rod, the stress is plastic region. Why do we need to stress this? In the elastic region, you can use the calculation. Sigma is equal to E epsilon to find the epsilon, and so. But when it is plastic, there is no equation. You have to go back to the graph. You have to go back to the graph and then solve it, right? So this is important. Therefore, in the part AB, sigma is equal to E epsilon. So epsilon is equal to sigma upon E. Sigma is this which we found. E is given in the problem as 70 gigapascal. Remember that all units should be correct. Mega is 10 raised to 6, giga is 10 raised to 9. So you find this is the strain. This is the strain. This is only the strain, not the change in length, strain. Then in part BC, we see that it is plastic region. So at the load of 10 kilonewton, right? At the load of 10 kilonewton, you go into the graph and roughly read the value of the strain. At that point, remember, not after the load has been removed. Just drop a straight line down, not a parallel line. Not a parallel line to the straight line region of the graph, a straight line down, vertical line. So this strain is roughly 0.05, right? So now this is the strain in the elastic part, and this is the strain in the plastic part. And we know that elongation, strain is delta L upon L. Delta L upon L. So delta L, the change in length, is a strain into the total length. So therefore, this is what we are saying, that the delta change in length. In one part, you see this is the value, and AB is 600 millimeter long. So this is it. In the other part, this is the strain, and it is 400 millimeter long, right? So the strain into the length, and therefore this is the total elongation, right? So this is the solution of this question.